Today I'm going to do lesson 4.1, solving systems of equations by graphing. And I kind of like this whole first page here because these essential questions I really like this time. It says, how can you use a graph to illustrate the solution to a system of linear equations? So each line shows all values of x and y that work for each equation. The intersection is the values that work for both. Intersection is the x and y values that work for both. Whatever x and y is at the intersection, those values you could put into both equations and they would work. So how does the graph of a system of equations with one solution differ from the graph of a system of equations with infinitely many or no solution? So let's look at what they'll look like. 1, 2, 3. All right, so one solution will look something like this, where they cross at one point. And they don't have to go opposite directions. They could both be going up, but one at a slower rate, and eventually they'll cross. A graph with infinitely many solutions will look like this. And no solutions means that they never cross. So those are going to be parallel lines. So one, infinite, and none. Infinite, they're the exact same equation, and that makes the same line. Sometimes the equations may look different and still actually be the same, like if one is written in standard form and the other one's slope-intercept. But then when you go to graph it and you see that they are exactly the same line, or you go to solve the equation some other way and you realize that the equations have exactly the same numbers, that they're modeled exactly the same once you move them around, then you'll see that they are infinite. So why is the point of intersection for a system of equations considered its solution? And that's because those numbers solve both equations. They make both equations work. And we're going to do a real world problem at the end that I think helps to see that. Riesz states that the system of equations has no solution because the slopes are the same. Describe Riesz's error. So we have one written in slope-intercept form and the other written in standard. So this looks like y equals mx plus b. This looks like ax plus by equals c. Slope, intercept, and standard. So these don't look the same, but if I rearrange this one to put it into slope intercept, we'll see what he's talking about. So to put it in slope intercept, I just want to move everything except for y to the right hand side. So I'm going to subtract my 3x over. 3x minus 3x will cancel itself out, and I get negative 3x minus 1. And see, this also says negative 3x minus 1. So it's not that it has no solution. They're exactly the same, so it's infinite solutions. All right, the next two we're going to graph. Solve each system by graphing. So I have one that starts at a 5 and goes up. I have one that starts at 0 and is going to go down. So this is y equals mx plus b. So slope, y-intercept. So I need to start at 5 for this one and go up, 0 at this one and go down. So let's see. I think it might cross backwards since they're going in such different directions, but I just need to have some room to graph. 1, 2, 3, 4, 5, 6, 7. I'm going to maybe put it here so I have 8 squares so I can